Hi everybody, finally getting around to this one. It was asked of me to do problem 32 from chapter 24 here. Alright, I'll read it here. It says, early black and white television sets used an electron beam to draw a picture on the screen. The electrons in the beam were accelerated by a voltage of 3 kilovolts. This is actually very similar to the oscilloscope that I showed you guys in the demonstration a few weeks ago, or a couple weeks ago. The beam was then steered to different points on the screen by coils of wire that produce a magnetic field of 0.65 Tesla. And then it says, what's the speed of the electrons in the beam? All right, well, in this case, I'm going to draw a quick little picture here. So if I had, you can kind of think of like having kind of two plates with maybe like a hole inside of it. It's going to speed these things up, kind of like our mass spectrometer. And so electron, you're going to want probably positively charged plates over here, negatively charged plates over here. And so we'll get our electron, let's make it a different color, something like that. So there's our electron, and then it's going to reach eventually here. It's going to go through the plates, and it's going to have some speed afterward, like that. So there's the speed that we got. Basically, remember, electrons fall to low potential. So let's say this is a potential of 0, even though, right, we're near a positive charge. I'll just say it's a potential of 0. This will be a potential of 0. So even though it's a negative charge, it'll be at a potential of 0. And then I think I might have misspoken. If I did, electrons fall up in potential. So this is going to be a high potential that's 3 kilovolts or 3,000 volts is going to be up here. So that's 3,000 volts right here. We're here, yeah. So here is our initial moment. We basically have, yeah, and then here's our final moment. All right. Let's see, so it says, what's the speed of the electron? So I think what I'm going to say is, that's what I wanted to say, is that the velocity here is equal to 0. Careful, velocity is small v, voltage is big V. Sorry, here, I'll try and make this V a little bigger. There you go. So I'm thinking I can use the conservation of energy here. So yeah, that's what I'm going to do. So my initial energy is equal to my final energy. And then instead of, I'm going to kind of go about this a little bit of a quicker way. Instead of kind of addressing what my initial energies and final energies are, I'm just going to say, well, what type of energies are being changed here? So essentially the energies that are being changed here, I got a change in potential energy here, electric potential energy, but then I also have a change in kinetic energy as well. And so in my conservation of energy thing, I'm just going to add in potential energy. So here's my initial electric potential energy plus my initial kinetic energy. And then it's going to, at the end, I'm going to have some final electric potential energy plus my final kinetic energy. All right. So potential energy from my equation sheet is equal to Q times the voltage, where kinetic energy, hopefully we got that, is 1/2 mv squared. So voltage, going to make that big. There we go. However, right, the voltage here is 0. So the voltage at the beginning is 0. So at first, the electron has no kinetic energy. It's not moving, and it's at my 0 moment. So both the potential energy and the kinetic energy are going to be 0 here. Where at the end I will have some potential energy and some kinetic energy. Let's see what that looks like. So I got 0 equals the potential energy is the charge multiplied by the voltage plus the kinetic energy, which is 1/2 mv squared. So it's the speed of the electron squared. And I'm trying to find out the speed. So I'm going to isolate this. So that's going to give me negative QV times 2. So I'm going to do some quick maths here. and this, and then I'll take the square root of all that, and then I got v. So now I'll plug in all this. That's going to be 2, negative 2, times the charge of my electron, which is negative 9. That's the mass. Negative 1.6 times 10 to the negative 19 coulombs. And then I'm going to multiply that by the voltage, which I got 3,000 volts that I have at the final moment. There we go. All right. And then divided by the mass. Now I can plug in 9.11 times 10 to the negative 31 kilograms. And I'll get the speed of my electron. Let me plug it in here really quickly. Let's see, 1.6 e to the negative 19 times 3,000 times 2 divided by 9.11 times 10 to the negative 31. And then I'm going to take the square root of all that. And I'm getting 1, 2, 3, 4, 5, 6, 7. So 3.25 times 10 to the 7 meters per second, which is okay. That's under the speed of light. So and that could give me a hint that I might have a mistake. And there we go. So there's my answer, kind of using the conservation of energy there. All right. Then it says, what acceleration do they experience due to the magnetic field, assuming that it is perpendicular to their path? What is the acceleration in units of g? So what acceleration do they experience due to the magnetic field? So basically, this charge now, so here's part B. This negative charge is now going to show up in the presence of a magnetic field. So let's see. Let me really quickly here. Let's say the magnetic field is pointing into the page. So the magnetic field in which it resides is now going into the page, and it's moving like this, right? Well, it's going to feel a force, and that force is going to cause it to move in a circle. Let's say something. It's a terrible circle, but you get the idea. And the circle has a radius r. Let's say. So and we're trying to find out the acceleration acceleration due to the magnetic field. All right. So I think what I want to do, is I'm going to use F net equals ma. Let's try that first. So F net equals ma. We're trying to find out the acceleration. So the net force is really just going to be the magnetic force. That's what's causing the centripetal acceleration here. Here's the speed v, and this v is basically going to be that v down there. So F net is really just my magnetic force. That's going to be mass times acceleration. The magnetic force is QVB sine theta, which equals my mass times acceleration. Then I'm going to divide both sides by mass. The other thing I can recognize here is that my displacement is always perpendicular to my velocity. So I'm sorry, the magnetic field is perpendicular to the velocity here. So that's what they told me to assume. So they told me to assume that back here. All right, then that basically means this sine theta has to equal 0. So I'm going to divide both sides by the mass of the electron. I think I'll be able to solve this. Let's see. So charge of an electron is 1.6 times 10 to the negative 19 coulombs. The velocity I got was 3.25 times 10 to the 7. Magnetic field, they better have given me that, 0.65 Tesla. And then lastly, the mass of the electron is 9.11 times 10 to the negative 31 kilograms. Plugging all that in, 1.6 times 10 to the negative 19 times 3.25 times 10 to the 7 times 0.65 divided by 9.11 times 10 to the negative 31, and I get 3.71 times 10 to the 18. Yikes, that's a lot of acceleration. Poor electron. And then they want me to get it in terms of g's. How many g's is that? Well, basically, I would divide this by 9.8 or 10. If I were just divided by 10, that basically tells me that the acceleration in g's is 3.71 times 10 to the 17. I mean, that's an insane amount of g's, right? So, yikes. But if you want to get more accurate, you could divide it by 9.8, and that'll give you a bit more accurate way, but I'm just moving along here. So, all right, now for part C, it says, if the electrons were to complete a full circular orbit, what would be the radius? All right. So I'm going to use this same thing here. Continue on. I'm actually going to just continue on from here. So this basically said QVB equals, make it a different color. QVB equals m times the acceleration. So that's going to be QVB equals the mass times, if I'm moving in a circle, it's going to be v squared over r over the radius. And that's the radius that I'm looking for. This velocity cancels out, so both of those are speeds. So those will cancel out. I'm going to isolate r, so multiply both sides by r, divide both sides by q times b. It's going to give me mv divided by q times b. It's going to give me the mass of an electron, which is 9.11 times 10 to the negative 31. The speed, which is 3.25 times 10 to the 7. And then the charge of an electron, which is 1.6 times 10 to the negative 19 coulombs. And the magnetic field, again, which was 0.65 Tesla. So once again, plugging all this in, I'll get my radius. So 9.11 times 10 to the negative 31 times the speed, 3.25 times 10 to the 7. Divided by 1.6 times 10 to the negative 19 times 0.65. And I get 2.85 times 10 to the negative 4 meters. All right, there's my radius. And then finally, I'll just answer this one without writing it down. It says a magnetic field can be used to redirect the beam, but the electrons are brought to a high speed by an electric field. Why can't we use a magnetic field for this task? So yeah, electric field caused them to accelerate, which gave them that new speed. But again, the magnetic field, the magnetic force, always points perpendicular to the magnetic field and velocity vectors. So basically, the magnetic field cannot do work on these, so it cannot increase or decrease the kinetic energy of it. It can only change the direction of it. So that's essentially why the magnetic field cannot do it. All right, hope that helped. Bye.